In this video, we're going to talk about pointers. We'll discuss the additional flexibilities and challenges that pointers bring to programming. Here in VS Code, I have a very simple program that declares and initializes two integers, x and y. Now, what is a pointer? Well, a pointer is a variable that stores the memory address of another variable. In other words, it points to that variable. So let's declare and initialize pointers that will store the addresses of our variables x and y. So what I'm going to do is I'm going to copy and paste the declarations that we have. And then, of course, we would need to use different variable names. So we'll use p for the pointer that's going to store the address of x. And then we'll use q for the pointer that would store address of y. Now, so far, we are, of course, declaring p and q as integers. To declare them as pointers to an integer, all we need to do is to place a star right before the variable name. Like this. So now we are declaring p and q as pointers to an integer. Which is, of course, why VS Code started to complain right away, because 1 and 2 are not valid initial values for pointers. What we need to store into p is the address of x. And this is where the address of operator comes in. If we place the ampersand right before the variable name, we would fetch the memory address of that variable. So now pointer p is initialized to the address of x. And likewise, we'll initialize q to the address of y. Now, let's put in some print statements just to get an idea of what all of this is going to look like. So I'll do cout, and I'm just going to print the values of all the variables that we have. And of course, for the first two, it's not going to be very interesting, but we'll just do it anyway. So I'll copy and paste this 4 times, and then we'll change all of this to y, p, and q. So let's save this and compile and run it. And this is what we have. So x and y are 1 and 2. No surprises there. And then the value of p, this would be the address of x. And then the value of q would be the address of y. So when the compiler compiled and stored this program in memory, it placed x and y at those addresses. And it makes sense that they're just 4 bytes apart, because 4 bytes is how big an integer is. And so then we fetched those addresses using the address of operator, and we stored them into the pointers. Pictorially, what this looks like is that we have declared x and y to be 1 and 2. And then wherever the compiler stored x, let's actually have a look at that. It was 340. Okay. So this memory location ended in 340. And then y got stored in the memory location that ended in 344. And then those were the values that we actually stored into the variables p and q. Because p and q respectively point to x and y. So the next question is that if someone was to give us a pointer like the pointer p here, could we somehow follow the address that's stored into the pointer to figure out what's there at that address and then do something with whatever is there? And the answer is yes. I mean, that's the whole point of pointers, no pun intended. And this is where the dereference operator comes in. And the dereference operator is also a star. However, this time we are not using the star in the declaration. So if you place a star before the pointer variable, like this here, this means give to me whatever is stored at the address that the pointer is pointing to. Once again, this is not the declaration of P like it was on line 11 and 12. This is a different use of star. So I'll put this in the print statement just so that we can verify how this works. So I'll write value of star P, and I'll put star P here. And then likewise we'll do with Q. And we'll save this, and we'll recompile it and run it. And we can see that the value of dereferenced P is 1 because P was pointing to X. And likewise, the value of dereferenced Q is 2 because that's where Q was pointing to. It was pointing to Y. Now, beyond just reading the values that are stored at the memory locations pointed to by pointers, like we did up here on lines 20 and 21, the dereference operator could also be used to change what is actually at those memory locations. It could be used to override things that are pointed to by the pointer. So we'll do this here. So we'll change the value at the memory location pointed to by P. And I'll just do dereference P equals to say 3. And I'll copy and paste my print statements just to see what's gonna happen now. So we'll just say that this is after the change. Okay, so let's compile and run this. And after the change, the value of X is now 3. And that is because on line 24, we said, let's go to the location that P points to, which is what the dereference operator did. And let's change that to 3. So pictorially, what we said is that let's get rid of this, and this is now going to hold 3. Now, something else that we could do is we could, of course, reassign the locations that pointers point to. So let me do this here now. So I'm going to say change P to point to the same location as Q. And all we would have to do in this case is just say P equals Q. And then we will copy and paste our print statements once again to verify how this looks. So I'll say after the reassignment of P, I'll save this and I will recompile and run. And we see that after the reassignment, P and Q do point to the same address. Of course, every time that I recompile the program, the addresses would keep changing because the compiler puts things into different spots in memory each time. However, all we're looking for is that before the change, the addresses were different. They were off by 4 bytes. After the change, P and Q point to the same address. So pictorially, what we did is we said that, okay, P, you're no longer going to point over here. And now you're just going to point to the memory location that Q was pointing to. And we haven't dereferenced anything, so we haven't changed the values of X and Y. But we can do this. So I'll copy and paste this line here. And I will just say that dereferenced P points to 10. And I'll copy and paste the print statements. And I'll say that after reassignment of P and change to 10, and we can recompile this once again and run it. And now we see that the value of Y has changed to 10 because that's where P was pointing to, so that got changed to 10. So pictorially, what we've done, I'll put this in, say, green, is we have folded P down to here, and we have changed this to 10. Okay. Working with pointers becomes a lot more interesting and useful once there are functions involved. What I have done here is I have cleaned up the file that we were working with so far. All there is left are the declarations and assignments of the two integers, and then the declarations and assignments of the two pointers, and a set of print statements. I have also added a very simple function add that takes in two integers as parameters, and then it computes their sum and stores the sum into X. Do note that the function doesn't actually return anything to main, it just has a void return type. So let's call the function right here before the print statements, and we'll give it our integers X and Y as arguments. We'll save this, and we'll recompile and run things. And we see that the values of X and Y are still 1 and 2. So as far as main is concerned, nothing happened to them. And this is not too surprising because, as you may remember from Java, that primitives, such as integers, get passed to functions in by value. So all the changes that happen here in add are local to add. Surely X got updated, but it's just a local variable and it wasn't returned back to main. So let's have a look at what would happen if we were to use pointers. So I'm going to copy the implementation of add, and I will change the parameters into pointers, and I will add the dereference operator to all the elements of the sum, and then we'll copy and paste this, and now call add with the pointers P and Q. And I'm using the same names here, but the signatures get overloaded. So as soon as I give P and Q to add, we know that it would be the pointer version that's gonna run. And then I'm just going to put a print statement here that this is the result of the pointer version. And save things and recompile and run, and now we see that the value of X in main did get updated to 3. Because what happened here is that as we passed in the pointers, on the right hand side the dereference operators were used to fetch the values that the pointers were pointing to, and on the left hand side the sum was stored into whatever was being pointed to by pointer X, because there we also had the dereference operator. So pictorially, essentially, on the right hand side we have followed both of the pointers to X and Y. And then on the left hand side, we just follow this pointer to store the updated value of 3 into here, like that. So as you can see, you can use pointers to sort of implement in the pass by reference schematics in a way. Now, let's see what would happen if we tried to reassign the pointers in the pointer version of add. So what would happen if we placed a line like x equals y here, where we essentially trying to say, well, let's get x to point to the same location as y. So, and then we do already have the call to the pointer version here. So we'll save things. And then we'll go to the Linux shell, recompile, and run things. And we see that after the pointer version, P and Q still point to different addresses back in main. So as far as pointers are concerned, this here, once again, was just local to the function add. The changes never made it back to main. So the way that we can fix this is with the use of double pointers. So it would be a double pointer is a pointer to a pointer. So here we'll define double pointers, and I'll call them A and B. And we'll get A to point to P, and then B to point to Q. Now we'll use double star to define a double pointer. And then in here we'll assign the address of P, and in here we'll assign the address of Q. And then let's make a double pointer version of add. So we'll change the parameters to double pointers. And then let's comment this out for now. And we'll place the dereference symbols on X and Y. And we'll make a call to the double pointer version down here. So this time we'll pass A and B. So this will be the result of the double pointer version. We'll save things. We'll recompile and run. And now we see that after the double pointer version, P and Q point to the same address. So this change here did propagate its way back to main. And now we can comment this out, but if we still want the addition to happen here on the values, we have to add another star to have sort of like a double dereference operator. So we can save this. I can clear the console, recompile, run, and now we see that x is 5, which was the sum of 3 and 2. Pictorially, what we have here is, of course, we have A pointing to P, and then P points to X, and likewise we have B pointing to Q, and Q points to Y. Okay. Working with pointers, the way that we have done in the add function, could simplify the implementation of functions that need to return several values. Let's take a look at the function foo here. It wants to update the values of 3 integers. The integers are passed in by value, so of course all the changes here are just local to the function foo. Now, we could return the changes, however, we are limited to just a single return variable. One approach would be to define a struct, bundle up the updated values into a new struct, and then just return the struct. And then we would need to take the struct back apart in main to access the respective components. This approach certainly works. However, there is a way that you could also do this using pointers. So we declare pointers A, B, and C, and we assign them to point to x, y, and z respectively. And then we have the version of foo here that accepts, this time, integer pointers as parameters. And then it uses the reference operators to update the values of those pointers. And we make the call to foo here with the pointers that we have created. Both approaches work, and perhaps this one is a bit more elegant. By the way, this is something that you wouldn't been able to do in Java, because in Java, essentially, as far as the primitive values are concerned, they're always passed in by value, and there's no way to get around that. Pointers do really bring additional challenges and dangers to programming. I'm back in the main file, and here I have created the function foo, which declares and initializes an integer v, and then declares a pointer w to that integer, and then we return the pointer. So the return type of foo is an int pointer. Down here in main, we make the call to foo. We save whatever is returned into this pointer read from foo. And on the following line, we try to print the dereferenced value of that pointer. We might sort of expect that that would be 1, because if we trace all of this back, that pointer would point to this integer here, which is 1. So let's try that out. And we don't get 1. We get some garbage value. So why is that? Well, this v here is a local variable, and it will go out of scope. It will get deleted as soon as foo returns. So by the time foo returns, the space in memory gets allocated for something else. However, the pointer w still points to the spot in memory. So by the time we are back here in main, we are actually going to that address that used to have v, but instead there is something completely else there, which for us is just some garbage value. Now, what else you could do is you could, for example, declare a pointer and then not initialize it. So I'll copy and paste this here, and we'll try to print the dereferenced value of this pointer c. So let's see how that works out for us. Clear the console, recompile, and run things. And it's telling me that the dereferenced value of c is 1. But I actually don't know where that is coming from at all. So another thing that could happen is that, which is even worse, is that you can try to dereference a null pointer. So then I'll say that I'll try to print the dereferenced value of d. And I'll save this, and we'll clear the console and compile and run things, and we completely fail. So it says here that we segfaulted, which means that the program has encountered a critical memory error and had to quit. So if you had anything else in your program after this, it wouldn't run. You can also see that the dereferenced value of c turned into something very bizarre. So those are some of the issues that you can run into with pointers. And here, of course, I'm sort of making them up on purpose. However, you can expect that as your code gets quite complex, those issues could happen sort of as you have recursion, as you have for loops that are going in all sorts of different directions. those issues can happen behind the scenes and can cause issues. But in general, don't dereference null pointers. Do initialize pointers right away. It's always a good idea. By the way, in Java, this would not even compile because Java requires you to initialize your variables right away. Not that Java has pointers, but you can't just declare an integer in Java and then sort of leave it. But in C++, essentially anything goes, and there isn't much help from the compiler to detect things. Because note that all of the errors that happen here were not detected by the compiler. They only came up once you started trying to run things. So yeah, so don't have null pointers, don't have any initialized variables, and finally, do not ever return a pointer to a local variable from a function, because those variables go out of scope, and then you would be shooting into memory addresses that don't make a lot of sense. Finally, let's talk about how do pointers work with classes. What I have here is the declaration and implementation of a very simple, silly class. It comes with fields of name and ID. It has the getters. It has the constructor. Now here, I haven't bothered with the header file, and I just collapsed the declaration and implementation all into one. It's perhaps not the best programming practice in general, but it's certainly something that could be done and something that does work, and is perhaps appropriate for simple, short classes. Something else that I want to show you here is the shorthand notation for the constructor. Right here. So you have the typical signature of the constructor, and then you place a colon, and then you just outline how do the constructor parameters map to the fields. So you say that name maps to name, and ID maps to ID. Then the body is empty. If your constructor was to do some custom things, you could have a body and you can have those things in the body. However, if you just want a simple mapping of the parameters to the fields, this is all you need. Okay, so let's construct an instance of this class. We'll call it S, and I'll just give it hello for name and 1 for ID. Now, let's declare and initialize a pointer to point to this class. So I'll say it's done exactly the same way as we have done with the integers. So I'll say sample class star, and I'll call my pointer P, and I'll set it equal to %s for the address of S. So now let's try to access the class through the pointer. So I'll do a cout, and I'll say that result of getName is okay. So now we want to put something here that is actually going to call the getName method on the class, and I want to do that through the pointer. Well, what you would need to do is you would need to dereference the pointer P, and then you would need the dot and just call the getName method. Now, here the VS Code is complaining about this, so it's not quite right. What's missing is you need parentheses around the dereference P. And that is because what happens is that you want to make sure that P does get dereferenced first. Essentially, the parentheses here are to ensure the correct order of operations. So let's just save this and compile and run things, and we see that we do get the hello. Now, this notation here could be kind of annoying. So there is a shorthand notation that you use to do things, And it is just to say P followed by the error. So all we do essentially is we replace the dot by the error. But this notation here is equivalent to this one here. It's just a faster way to do things so that you don't have to remember, well, where do the parentheses go, and so on and so forth. So we can save this and we can run it, and we see that the result is still the same. And this now explains that weird notation that we had to use when we had this in the constructor. And that is because this is the keyword this is the pointer to the current class that you're working with. So just pictorially, to emphasize what happens here, is that you have your pointer P, and the first thing that you need to do is you need to dereference your pointer. So this is where the star comes in, and that just brings you to the class. And then you use the dot. To actually make your way through the class to the getName method. And that's why the parentheses are so important in this notation, that you actually want to dereference P first so that you get yourself to the class, and then offset within the class using the dot to the getName method. But both notations are equivalent, and this is much easier to remember here. So I would just like to mention a couple of asides to wrap things up. When you see me declare pointers, you might have noticed that I placed the star adjacent to the name of the variable. So let me just declare a new one here to illustrate things. So I'll declare an int x and then a pointer y to point to x. And you can see that the star is adjacent to y. In other places, you might see the star being placed adjacent to the int, or adjacent to the name of the class. And as far as we are concerned here, it doesn't matter. White space doesn't matter in C++, so you could even put a space in here, and things are okay. So then, where the confusion could come in is if you're trying to declare several variables on the same line. So for example, if I wanted to declare integers a, b, and c, I could do it like this, where I just write int once, and then expect a, b, and c to all be integers. If I try to do the same thing with pointers, and what variables haven't I used? I could use q, r, and t. What happens here is that it's only q that gets declared as a pointer, and then r and t get declared as just regular integers. So then you need to place stars somewhere in here to make sure that those do get declared as pointers. And by that point in time, you might as well place your stars adjacent to the name of the variables so that you're not confused. However, an approach like this is certainly fine, and it's certainly fairly widely used because you're usually just sticking to declaring one variable per line, and no issues there. Another thing is that let's talk a bit about avoiding null pointers. So let's say that if I initialize t to be null, then it's usually a good idea that whenever you're working with pointers that could be null, to just wrap things into an if statement. And then here we'll put that pointer t is not null. And then for else, we'll put down that pointer t is null. So this way that if you do run into a null pointer somewhere, at least you don't completely crash. I mean, there is a way to debug segfaults and all that, but at least you don't completely crash. You might get caught in some print statement that would help you to understand where exactly you ran into the null pointer. So let's just save this and compile and run it. And we see that, we did set pointer t to be null, so we do print a line that pointer t is null. Because if pointer t wasn't null, then this would have had a non-zero value, so then it would have went into this part of the if statement. Okay, so to summarize, first we discussed the pointer basics, like how to declare one and initialize it. So we talked about the use of ampersand as the address of operator, and how we need the star when we are declaring pointers. And then we talked about the dereference operator, which is the use of the star elsewhere other than in a declaration, and that follows the pointer to whatever address is stored in the pointer. And then we talked about the different ways that we can work with pointers in functions. In particular, we had the 3 different implementations of the add function, where the one into which we just passed in regular ints, there it returned nothing to main and did nothing as far as main was concerned. Once we changed the parameters to pointers, then we were able to update the variables, but we weren't able to reassign pointers themselves. And then once we went to a double pointer, then there we were able to update the pointers and reassign them. We talked about the dangers with using pointers, such as not returning an address to a local variable. It's always a good idea to initialize pointers, and it's always a good idea to check for null pointers so that you don't dereference one and crash. Finally, we talked about how pointers work with classes. I just mentioned about this short form of the constructor that you could use. And then we talked about how to dereference classes, and that those 2 ways to do this are equivalent. Okay, thank you.